Can people at home hear me okay, or at least tolerably? Again, the microphone is not connecting. Okay. I'll try to remember to help us about this after class. Somebody's welcome to remind me. Okay, last class we started talking about linear discriminants. We moved from Fisher over to linear discriminants. Okay. We're talking about how if there were two classes, X's and O's, if we can have a linear decision boundary, we'd like that decision boundary to put X's on one side and O's on the other. Not too hard of a concept there. Where I confused you was saying it was a lot easier for us, instead of having the two conditions, which is choose one thing if we're in class 1 to be bigger than 0, choose the same thing to be less than 0 if we're in class 2. Instead of having those two statements, those if we're in class 1, if we're in class 2, one time we're greater, one time we're less than, having to keep track. So we were just going to take our X points, the feature values for them, negate them, and then we having good choice of decision boundaries, that's that line. We have a good choice of decision boundaries if X's and negated, or O's and negated X's are all on the same side of the line. That was the hard concept from last week. Is that we want to take these, change their features to negated. So rather than having them on opposite sides of the lines, these and the negated features will all be on the same side of the line. So if X's and O's on opposite sides of the lines, the O's and the negated X's will all be on the same side of the line. Then came, we had to choose where that red line was going to be. We decided we'd define the line by its normal, which means we could then talk about lines and planes and hyperplanes. And we want to move that normal around and that there was a region of different choices for that normal that would all result in X's and negated X's and O's and all being on the same side. There was not just one solution to the problem, there was a range of solutions. A range of solutions. Yes. We want to move X's and O's to the same side of the line. The question is, why do we want to do that? Because if we have them on different sides, we'd say that this product will be greater than 0 for O's, and this product will be less than 0 for X's. We have to have two different things in our code. If this, do this. If this, do that. If I negate those X points, the coordinates for them, and I move these guys, come on. I move these guys over to there because I've negated them. Each of these are basically negative X values. Now everything's on the same side, and instead of having two equations, one greater, one less than, now we have one equation greater than for all classes. We don't need to have these two equations, this condition if. We don't have to have sometimes greater, sometimes less than. We have for all points greater. Everything.
So if I'm understanding this correctly, this is useful for determining if the decision boundary is correct for
We're trying to determine the decision boundary of this big fat red line.
So if one of the x's not negated, but was on the other side of the line, we know that would be.
We know that would be an error. We want to reduce errors. And if they are linearly separable, it is possible to find a big fat red line where everything's on the same side. If they are not linearly separable, then there does not exist a big fat red line, which is able to put everything on the same side. Okay. So we're going to take one of the classes. We're talking about the two-class problem here. Take one of the classes, negate it. Now projecting all the points, that product. We want to compare everything greater than 0. Everything should be on the same side of the line. And if we're successful with that, with only that one condition to check, everything on the same side, everything positive, then we're good. So then the question we started on last class was, how do we find that red line? So we started off making an initial guess for a red line. You can make it anywhere. It has that normal vector. We can then check and see, is everything on the right side? And if somebody was naughty down there, if somebody is naughty and forms an error, he's on the wrong side of the line. I give that analogy of the cows being in the road in Idaho. They're on the wrong side of the fence. We want to do something. Rather than moving the cow back on the right side of the fence, we're going to move the fence. That's a real Idaho thing. I'm not from Idaho. So we can take whatever is wrong, and that whatever points are there, and this example has one error point. There could be lots of error points. But every error point is going to have an error vector. And we can take those error vectors and add them to that normal vector that describes our line, our plane, our hyperplane. And that will move our normal vector, and that will move our line, our plane, our hyperplane. Hopefully fixing things. Now, if we look at this example, once we moved it, whoops. Now the O's in the wrong direction. And if you know that whack-a-mole game from the carnivals, so we fixed one problem and whoops, there popped up another problem. So we're going to do a little bit of whack-a-mole. And the answer is that we're going to go through and iterate again and again and again until we get there. And maybe instead of adding the entire error vector, maybe we add a scaled portion of it. 50% of it, 10% of it, 1% of it. And that will move our normal vector less. And gradually we can find our way into the correct point. And sometimes we just have to do multiple iterations through that. And that led into this method called gradient descent that we talked about last class. We talked about being up on the mountain skiing, but it's foggy. At the end of the day, you need to get down to the lodge. Look around your local area. Where am I? Where's downhill? Take a step. Where am I? Where's downhill? Take a step. Where am I? Where's downhill? Take a step. how big of a step we take is eta. It looks like an N with a long tail, but it's really more like an I, eta. We've got eta, which tells you how big of a step am I going to take. What's the problem if you take too small of a step?
Takes you forever to get there.
Takes you forever to get down. What's the other problem? You can get stuck in a local minimum. What's the problem if you take too big of a step?
Overshoot.
You can overshoot. If you're skiing, you wind up off trail, in a tree well. Take too big of a step, you may not get where you want to go. You're going to go start skiing out of bounds. So it's that Goldilocks idea. You got to find just the right size. What's just right? Too big, too small, just right. But you have the basic algorithm. Take a step size, and you need to look downhill. Which way is downhill? Downhill is a gradient. Count 3, I believe you had gradients. Gradients are just a vector derivative. Derivative with respect to every variable you care about. And you're going to add up those values at every error point over all points. We then went over some code. What are these 3 things I'm underlining?
Exit conditions of the loop.
Say again, I think you're right.
The exit conditions of the loop.
Exit conditions. We're going to stop our search when one of 3 different things happens. Now, I've written it as a while loop, which means we're going to continue the search so long as none of those 3 happen. Well, you've had enough logic stuff from digital systems and whatever. So if any one of them comes true, we stop. What's the first one?
Iterations.
Iterations. We don't want to do this forever. Put us at your emergency stop. That should not be your primary exit. That's your emergency stop. Because we don't want to have code that's running forever. What's the second one?
Errors.
Error. What's that in our ski hill analogy?
Step size to get.
No.
No flat spot.
How far are you from the? Oh yeah, it was the flat spot.
No.
What's that in our ski analogy?
Oh, you
How close we are to the lodge downhill? Have we made it downhill? If we're downhill, let's stop.
Is
ERR is error. Very good. I named variables the same, sort of makes sense. ERR is error. We're going to set some sort of threshold that says, how close do we need to be to that ski lodge before we say, yeah, we're there. I don't need to do this anymore. We're close enough. And then the third condition, what's that third condition?
Step size. Right, or how much it has changed since the last.
How much has changed? Are we still actually going downhill? When you ski down, it starts to be kind of flat. There's no more downhill, you gotta start huffing it. So if we're down in the flat area, we're not making any progress. We're not gonna rely on gravity to get us there. We'll say, well, we're in that flat bottom area. Trying to take off the skis and huff it. we're done. We're not making any changes because gravity stopped. We're not moving based on gravity. No changes based on the gradient, no changes based on gravity in the hill. No, we're just gonna stop. When do you keep doing this and when do you take off the skis and just walk? So 3 conditions where we would stop gradient descent. Now this is a broad gradient descent problem. I'm just introducing you here to the broad gradient descent. This structure applies for gradient descent used in any application. So I gave you an example last class where we had a bunch of points. And we wanted to fit them to a line, straight line, y equals mx plus b. Our unknowns were m and b. So we started off with some random values for m and b. We want to iterate and change m and b until we find the m and b that gives us the best answer. So we need to calculate the gradient with respect to 2 variables, m and b. So that gradient is a 2-element vector. Our error is taking our data, subtract y equals mx plus b. So if we take, we know for each of these points, we know an x coordinate. That's our data. We know a y coordinate. So if we take those x values, multiply by m and add b, it tells you where that line would be. If I'm here, it would say, where is that line? And if I'm here, it says, where is that line? So for each data point, we have an x value with whatever m and b value we have for the line where we're at that point in the ski hill. We can figure the amplitude of it. And we can then compare it to where that line would be at that point. We take the square root of it, so negatives turn positive, so it doesn't matter if it's too big or too small. And that's how much error we have, and we're going to have it that for every point in our data. We're going to take each of these errors, add them up, square those errors and add them up, and that's our total cost for that line, our total fit for that line. You go to the store to buy a suit. You got an interview coming up, so you're actually going to dress up. You try a suit on. Well, it fits in certain places, doesn't fit in certain other places. You're going to take all that fitting and adjust until you find something that fits. So we got all those different errors for how big and tight it is. Take all those errors square them each and then add up the squares. Sort of like your Euclidean distance without the square root. We're going to take that, that's our total error across all our points. Take the derivative with respect to our first variable m, take derivative with respect to our second variable b, and you did this in class last Thursday. Should sound vaguely familiar. No, so the derivative, we add them up over all of our points. This is MATLAB, so we can just do it in one line. Otherwise, there'd be a for loop here. And you'd add these up across all the points. How many data points you've got. We then take those combined that's sum of your gradient, sum of your gradient. These are a sum. Put those two sum of your gradients together, you get your gradient sum. We're then going to update our estimate by our step size times the sum gradient. Update our estimate was with parameters, M and B, by our step size and our gradient. Then we go through and check. If we're after the first one, we're going to figure out how much difference we had. Are we still going downhill? Are we still making a change? Have we stopped moving? We check the old values, figure out what our guess is, figure out what our total error is at that point in time, and come back up and say, are we done yet? If not, we're going to take another step, figure out which direction we're going to go, readjust our estimates, and move. Over and over and over. Okay. Then I showed you an example with MATLAB last class where you can see that line moving and it wiggled and it finally stopped. And then you can see it on a curve where the points kept changing values. And at first they were all over the place and then they made it really smooth, working their way downhill. Then they got to the ski chalet. And they had a nice cup of hot cocoa and everybody was happy. So that example was coefficients for a line, M and B. A0, A1, A1, A2, depending on whether you have a 0 index array or 1 index array, M and B. Now we're going to use that concept, going back to that problem we were talking about, this guy, where we want to find the line that fits. So we detoured to introduce you to gradient descent. Raise your hand if that was new, gradient descent was new for you. A lot of it, so it's been a good use of my time. Okay. We're now going to use that gradient descent algorithm to gradually adjust the coordinates of this normal vector until we find our best line. Same procedure, but our cost functions now are all the points on the correct side of the line. And that's called a support vector machine, SVM. A lot of you I know have heard that term. Some of the papers you read in week 1 used SVMs. I've seen several of you mentioning SVMs. I'm not sure whether you knew what they were, but you're mentioning them. So a lot of you knew that they exist. They work pretty well. They only work for 2 classes. How many classes do we have in our project? 10. So for our project, you've got a couple of choices with that. I'm going to start it with 3. The example is 3. Let's see what I have a picture of that. Yeah, we'll come to that later. So we're starting with two classes. We'll come to what we do with more classes later. So all those points are coming from someplace, and we're going to try and draw a line. Bayesian detection says that we're coming from a density estimate. With those discriminants, you're working out where you have a probability. But with an SVM, we're looking more so at the actual raw data, similar to our K and M. We want to find a line. And the thing that really gets your SVM going is saying, who is closest to that line? Who's the biggest naughty student in the class? Dimitri, the naughty student, he said so. Okay. Usually I pick on Jacob, but Jacob's online today, so I pick on Dimitri. Okay.
I'm just telling that audio everything online.
So we want to find a line that can separate our 2 classes. It's done in an iterative fashion. And so if you have a lot of points, you got to figure out what to work with. In Bayes, we're going to use all the points because everything has different probability. So outliers will be just very low probability. And here we can weight them by how well they fit your data. Points that are really off in the distance are very well behaved. So they're like Charles sitting up there nice and quiet. He's very well behaved up there. Okay. And now we got Dimitri sitting here really close to the line. Troublemaker. And then we got on the other side of the line, we got Nathaniel sitting back there, being really well behaved. But close to the line, we got Fatma up front here. She's a real big troublemaker, even more so than Dimitri. I know her. And so whoever is closest to the line, we're going to say is going to be a little bit less well fitting. So we need to weight them more as a way of getting in and saying what we want to work on.
I see there's multiple lines on the block. So which line do we use to determine if we are close to the line?
Whichever one you're on in that iteration, trying to find the best one. So if I start with this line here, is that a line we want to end with?
No.
Why? Because Fatma's misbehaving. On the wrong side of the line. So then we move, we may wind up with this one next. That works. Got Fatma under control. Dimitri hasn't acted up yet, although he's thinking about it. But we might be able to find a better one than this, so maybe we try this one next. Because I don't trust that Dimitri's going to stay well behaved. He's too close in that border there. So we can maybe try this one. Okay, that's a little bit better. But now we got to worry about Remington. I don't know, we're getting too close to Remington. He might start having some problems there.
I mean, good point.
So then we can finally maybe settle on this one. where we've got everybody well behaved. And we're really far from there, so we don't need to worry about Faulkner, Dimitri, or Remington coming and causing problems, because of that big fat line at the end there is furthest from everything. So there's lots of choices for lines. Some of them are bad, outright bad. Watch out for Faulkner. We don't trust her. She's on the wrong side of the line. We don't want her to do that. And some of them are way too tempting that Remington and Dimitri are too close to that line, and we just don't want to be that close and leave them to that temptation. We know that given the chance, they'll act up. So there's lots of possible lines we could choose for a decision boundary. And the best line is the one that's furthest from all the points. So we want to find a line that maximizes the minimum margin, the minimum distance. We definitely want to minimize errors. We don't want anybody on the wrong side. But if we look for the points that are closest to the line, those are the ones that we really have to keep an eye on. I don't need to worry about Charles and Nathaniel. They're way back there. They can sit and surf on the internet and whatever. They're not going to cause any problems. They're way back there. But we got Fatna and Kristen and Dimitri and Remington. They're close to that line. I'm going to keep an eye on them. We want to stay as far from them as we can. The line is separated as much as we can. So these points that are closest to the line are our margin points. And the distance from those points of the line is our margin distance. And an SVM is looking through an iterative search built on gradient descent to maximize those distances. I don't want these guys acting up. And again, we have a cost function of how close are they to the line. We want to always optimize, minimize our costs. Ski downhill to that ski chalet, to the lodge, base lodge. Minimize those costs. Data points are just called support vectors. So you can think of them as being vectors instead of points. And if we just focus on the ones that are closest to the line, there's less computation. Okay, grad students, what does that remind you of?
Condensed data set.
Condensed K&N. Only thing that really matters is what's closest to the line, closest to your decision boundary. Charles and Nathaniel don't matter, they're off in the back. I'm just going to trust that they're not going to get into trouble there. What if they do? We've got big problems with our classifiers. But I'm really a lot more worried about Fatna, Kristen, Dimitri, and Remington. They're up front here, and I know that they're the troublemakers. So they're the ones which we're going to optimize on. So we can say we want to have a maximum margin classifier, keep those distances as big as possible. And those are the ones that we're going to be focusing on as we do our work. Those are our support vectors. Whoever's closest is our support vectors. You could also think about it as if you had a whole bunch of people trying to hold up a piece of plywood. Now, some of you are taller than others, right? Who's going to be doing the most lifting? The taller ones, not the shorter ones, the ones who are closest to that board. They're the support, they're the ones doing the support of that plywood. That's why it's called support vector machine, because we're focusing on those support vectors. The ones who are pushing most and supporting that line. The other ones are Charles and Nathaniel sitting in the back, or the short people not doing their lifting on that piece of plywood. They're there. They have to have the right class. But we don't need to worry about them because they're far enough away. You know, in that analogy of lifting the wood, you know, you ever tell people, just get out of the way, kids. You know, you're just in the way, you're not helping. So it's the same sort of thing. You know, yeah, I appreciate you wanting to help, but we'll just do it without you. They don't contribute to the decision boundary. Charles.
Does the number of points in each class look like metal with how many inactive constraints over active constraints all?
No, it does. Well, it does affect how many inactive they are, but only the ones that are closest are the active ones. And theoretically, only one per class is active. Because only one is closest.
So what are support vectors? Are they only one or is it?
No, they're from multiple classes.
So are all active constraints support vectors?
Right. Active constraints. The ones that are closest from both classes are the most active in the support vectors. And then we can determine the confidence by trying to minimize the distance between those points. And that leads to these zones where we've got space from that line. If things are linearly separable, those zones will be fat. We want to make those zones as fat as we can. To keep Fatma and Dimitri well clear from the boundary. So you want to maximize the margin together while minimizing the number of errors. There's a couple of different possible lines there. So what's the difference in this figure from what we've been talking about? The terminology for this. In this example, we can separate them with a line which is called
Decision boundary.
the decision boundary. And these two classes, because they can be separated by a line, are linearly separable. What about here? These two classes, the circles and squares. They are not linearly separable. There is no way that I can get both Dimitri and Fatma to behave at the same time. I've got to pick. But I'm going to go with that picking, which one I'm going to deal with also trying to keep Kristen and Remington there. So I've got these two to worry about. But then I'm going to take the Kristen and Remington, who are a little bit better behaved than Fatma and Dimitri. I still want to, I don't have to worry about them crossing the line, but I want to still keep away from them. So we're going to both minimize the error and maximize the distance. Maximize the margin of distance while minimizing the number of errors. So we can also count in an error account as part of our cost function, which goes into that derivative stuff, which goes into the gradient descent. And we're going to scale that by some amount. How much do I worry about Fatima and Dimitri? And how much do I worry about Remington and Kristen? Well, maybe I don't care as much about Dimitri there, so that C will be smaller. But then again, maybe I'm really, really worried about Dimitri because I know him, I've had him in other classes, so that'll make that C bigger. Who chooses this C?
Me do.
The designers, that's you guys. So again, let's go back to the first week of the semester. Infinite monkey theorem. There's code out there for SVMs. It comes with some default values, but it comes with these parameters you guys can set. When do you choose the default value? When do you set it yourself? Make them complete. And I'm recording.
Yeah, you're recording.
And you guys like that.
You're no longer sharing.
Yeah. I had to get back to my control screen.
Oh.
And then find the sharing screen. Okay. So when do you take the code and use the default parameters? And when do you take the code and you set your own parameters? Depends. But what are some of the things on which it depends? Here's a, it depends is not an adequate answer standalone.
If you need to figure out which type of error is less costly to make.
What type of error is less costly? How much is your job worth? How much does it matter if you mess it up? If it doesn't matter, just take what's there. If it matters, you better know what those parameters mean. You better make sure you've got the right ones. So we've been through the Bayesian classifier, or through the K&N classifier, where you're able to choose your ends. What other things could you choose for K&N?
If you condense it or not.
Was it a condenser or not?
Ties. Ties.
How to handle ties? What else?
How to calculate distance.
How to calculate distance?
How many neighbors?
How many neighbors? And now hopefully you've got a better feeling for what those decisions mean. There are options in code. Code is out there. When you leave here, it's fine to use existing code. There's nothing wrong with you using existing code. But hopefully through the project, you now understand what it's doing. And you're starting to be at a point where it says, oh, you've got these options. Which one do you want to set? You now know, oh yeah, I know what it does. Bayes, what options do you have for Bayes?
Dimensions.
How many features to use? But everything you've got how many features to use. You can use number of features in K&N too. Which covariance matrix to use? You've got options.
I mean, it doesn't apply to the project. Would it also be like what probability distribution to use as well?
Whether to what top probability distribution. So here I said use Gaussian, and generally Bayes is pretty much 99.9% using Gaussian. if it's a continuous variable. I did give you the example for the binary, in which case you've got Bernoulli. You've got options. Hopefully you're starting slowly to come together with understanding those options. And again, you'll download code. That's not a problem. Because I'm having you write code here does not mean that I'm against you using pre-written canned code. I have no problems with using that outside of this class. But you need to know how to use it right. I do not like infinite monkeys. You guys are a lot more intelligent than those monkeys. Not just randomly doing things. So you've got various parameters, and here, how to weight the errors is part of your decision. And when you've got that, then you've got things that are no longer just a simple quadratic thing, that optimization is a little bit more complicated, but the programming takes care of a lot of that. So you need to solve optimization procedures. Then it goes back to that discussion we had on Thursday of linear versus affine. What was the difference between linear and affine last week?
Origin versus node.
Whether you're a straight line, that from algebra you were told was linear, whether that straight line goes to the origin or not. And there's ways of cheating around that. We've already talked about being positive or negative as case and constraints. So we'll see this again later. If we have just one variable, and I'll describe this to people at home in a minute. We have just one variable. I've got a straight line with 3 O's on the left and 3 X's on the right, all on the straight line on your x-axis, for instance. If we say our origin is between the two of them, a straight line in one dimension is just your threshold, like you use in Bayes, one-dimensional Bayes in homework 3. Now let's consider another example. I still got 3 O's on the left, 3 X's on the right. But now those O's are centering around 0. They're no longer all on the negative side of the 0. Can I make a linear boundary that divides those two classes? No, we cannot do the threshold through the origin. Does not work, we get some errors. But if we add one, we add another dimension. So now instead of them being on the x-axis, we bring them up to the y=1 line. So now all of our features have an x value and a y value. We've not added any more information because we gave all of them the same y value, y=1. But now we can draw a line through the origin that separates the two classes. Maybe those at home,
Yeah, they can.
can you see this?
Yep.
With the camera?
Yep.
So now we can draw a line through the origin, which is linear, that goes through the origin, not a fiend. A fiend would be there, where our threshold is not going through the origin. The threshold is not going through the origin. By adding a dimension, even though that dimension is a constant, we can change the problem from a fiend to linear. And by the way, linear is good. Mathematically, a lot of things are nicer if it's linear. And we sometimes call that second dimension a bias. And this is a place where bias is good. Adding an extra bias can give you the other dimension, get us out of there. So we can add some extra bias. Another dimension allows us to get through and still use linear instead of a fiend for our answers. So it takes us extra points, keeping things close, but it also worries about the other neighboring points. So we got an error point, they'll have a weight. We'll just figure out how much that weight's going to be and how much error we're going to deal with. Okay, I was talking to you earlier. What about multi-class classification? SVMs work for 2 classes. In your project, you've got 10. Here's an example with 3. How do we do an SVM if we have multiple classes, more than 2 classes?
Would be like 2 classes and 1 class, separate those first, and we have 2 classes, so there's separation.
Perfect. Take 2 classes versus 1 class. So we're going to call teams, and maybe the triangles and squares are going to gang up against the circles. So we'll do that.
In this case, would it be easier to be circle, triangle on one team and square on the other team?
He wants to know if you can do circles and triangles on one team and squares on the other team. You could do that. Going through that, we'll get you one that goes through the origin, but we know we can always just add another dimension. So there just has to be a linearly separable, and we just add a dimension. So we go from the fiend to linear. So the problem is that we have 3 classes, not 2. And I challenge you to draw any one straight line that can separate that into 3 groups. Agree there's an issue? One straight line just won't cut it. So one way in which we use SVMs is called one versus all. We're going to call teams. We're going to simultaneously learn how to separate the circles from the triangles and the circles from the squares. This is sometimes abbreviated OVA. You'll see that notation in papers, in code. Whereas instead of having teams, we're going to take those circles and they're going to first compete against the triangles, and then those circles are going to compete against the squares. And it works. And you need to have 2 answers. What do you decide over here? You don't really know. Do it through that same process. So you're going to train K classifiers. And those trains are going to be just looking at the pairs, one versus the rest, the other versus the rest. And so you're really going to have circles versus triangles, circles versus squares. And then you're going to do squares versus circles and squares versus triangles. And then you're going to do triangles versus circles and triangles versus squares. You got to take everybody's against everybody else. So that's going to be k by k minus 1 over 2 total different combinations that really matter. Some of them are redundant. And then you do the prediction and you can vote between them. Come up with the answer. And the good news is that code for this is already built into any of the classifiers you download for SVM. But you need to know what OVA and what OVA means. You need to know what that means. And then there's 1 versus 1, where you go through and we're looking at the taking teams. You can do teams, you can do individually, 1 versus all, 1 versus 1. And you combine all those classifiers, and you can then find a way of dividing up your space. So that this is the circle zone, this is the triangle zone, this is the square zone. You're gonna have these boundaries, you stay over there, you stay over there, I'm gonna stay over here. And this defines where your decision boundaries are, and you're gonna wind up with basically 3 boundaries, and there's different ways of coming up with them. Okay, I already talked about mapping. If things are not linearly separable, here's an even more challenging case that I drew on the board. One line doesn't work. So just adding a constant didn't work. But we can take everything and add another dimension. Instead of adding a constant to everybody, the bias, we can take our variable x, we can take our variable x squared and create a second dimension that's x squared. And now you can draw a line there. It's a theme, but you can then do the bias to get above that. Yes.
Is it not just as easy to have a line that would separate 2 classes before adjusting that wouldn't be a linear line?
You could create 2 decision boundaries. One here, one here.
I was meaning so in the way that you've transformed to go from the linear or the flat case to a parabola shape, could you not just draw the same parabola shape that would separate, albeit without it being a linear separate?
I'm not sure I know what you're asking. So in this example, we take our x values and instead of adding the constant like we did on the board, we're going to make our second dimension x squared.
So he means something like that.
Yeah. So you could just have your separator as the x squared.
But that's not a linear boundary.
But is it not less work than having a?
It would be less work, but it wouldn't be an SVM, which only works on linear.
Okay.
2-class linear. So if you go back to Bayes, for a Bayesian classifier, think homework 3, you can have a straight line boundary. You can have 2 parallel line boundaries. You can have 2 cross line boundaries. What else can you have?
Every conic section.
All different kind of sections: circles, parabolas, ellipses, hyperbolas. So if you switch to Bayes, you can have quadratic boundaries. And thank you whoever wrote on the board. Okay. But if we're talking SVM, SVM only works with linear or affine. We have the bias. So therefore, we cannot have a quadratic decision boundary. It has to be a linear decision boundary. So the cheat is rather than draw a quadratic decision boundary, we create a new feature which is quadratic. We feed it into our linear classifier. So instead of having one feature, we now have two features, one of which is x, one of which is x squared. Okay. And this is very commonly done with SVMs. It's something you see a lot. Is they talk about you want to put in squares, you want to put in cubes. You can make it a cubic, take your feature and cube it. You guys have taken a lot of math. There's lots of choices out there. Quadratic is nice because it lets you have the two ends. And they just keep adding features, which are just linear, are different combinations of the already existing features. Kind of the opposite of Fisher, where we combine them to reduce features. Here we increase them, increase the dimension, and the net result is in an increased dimension feature space, we can have a linear decision boundary. By increasing the dimension of our feature space, we can have an increased decision boundary. We can still have a linear decision boundary. So these are mathematical tricks that are applied in lots of different places. Here's a nice one. Switch to polar coordinates.
Oh, man. Oh, no.
Told you, you guys have had lots of math. Now, the good news is the fact that there's people out there who've already been doing the thinking of this. What you need to do is understand why they're doing it. If you understand why they are doing it, then you're good. You don't need to be quite as creative. You just need to be understanding. But you get the point. You have your original features. We can do things to them that will then help you get to that linear decision boundary. That's so important if you're going to use an SVM. And generally, if you look at code that's existing packages, they've got your original x1, x2, and your x1 squared, and x1 times x2, and e to the x1 times x2, all sorts of things to allow you to get really oddball boundaries. But that oddball boundary is a hyperplane in this increased dimension space. Now in two-dimensional space, it's this really squiggly, wobbly, curvy line. But if we increase the dimensions using these nonlinear transforms, we can still get a linear decision boundary. From our linear classified, use our linear classifier. So that's what people have done for years with SVMs in order to use an SVM. And you'll see this trick here. Features or features or features, features or features or features. Everything goes there. But your dimensionality gets big very quick. It's still linear programming, so a lot of stuff is easy. You're doing transpose and multiply, but it comes out there. Okay. So how many of you have heard of SVMs before this class? You understand them better now? A little bit of what they're at? It's an iterative procedure to move that line, hit and divide things. Keeping Fatna and Dimitri in line. I'm worried about those two. Okay. It is a good tool. With the iterative procedure, it works pretty well. works best on a 2-class problem, but we can break it up into a higher number of classes by just saying, are we gonna do one versus each of the others, one by one, or one versus all? Making teams, how are we gonna divide up the space? Multiple little lines. But that also can make it computationally intensive, because if you've got 10 classes, well, now you gotta divide things up into 10 little pairs of lines, and there's all these different dimensions. And you've got 8 features, and if they're not linearly separable, those 8 are gonna turn into 16 or 32 pretty quickly, and you're trying to do it with those 10 classes. You see there's some complicated stuff going on. I'm trying to optimize across all these different cases. So it works. People use them because they work. I had a DACA student graduated a couple years ago, and he got here and he was totally set on how he was going to do it. I'm like, okay, well, let's play for a little while. I let him get some data. Then I let him, he wanted to do an SVM, so we did an SVM, and he got done with the SVM, and, but it worked. And we're like, yeah, okay, but now let's get the bigger problem at hand. Oh, yeah, this is not scalable. And then he was willing to take a different approach. So they work. I'm not saying throw it out. They do work. For many cases, they are used a lot. Just recognize where they're good and where they're not, and all the different things need to adjust. You need to decide which of these to use. The more you use, the more complicated it gets. But the more you use, the better the chances are you get it right, or get something that works. Okay. Decisions you need to make. Hand code out there, just beware. Understand what things are going on and what you're going to decide. There's a trade-off. The more you include, the more complicated it gets. And maybe we did not want to bend around these guys. Maybe we just want to live with that guy being an error. It's a bad piece of data. Instead, we built it up and we're now going to mess up all these other O's that we didn't know were going to exist. So you got to decide. We'll continue talking about that later this semester. If you're not done with Bayes, keep working.